or it won't be on the video. Okay, so yeah, since the end term test fails here, we don't know what's going on, right? So the only thing really left is the integral test. That's the only other thing we've talked about so far. So the integral test says that I need to try and show that if I can rewrite this right here as a function, right, of a real variable, I need to show that that's a positive. Yes. So I should put here integral test, right? So going off the sheet that I just handed you, is there one over there? Okay. The integral test says, look at the comments section on the side there. It says, the function f obtained from letting your sequence become a function of n must be continuous, positive, decreasing, and remember we said last class, by decreasing we meant eventually decreasing, all right? And readily integrable. So, oh, I stole this off the web. I just got on Google today and did a Google search of series tests, and this was the best one that I could find. It matched most of our formulas in the book. So I'm not taking credit for this, just so you know. But no one apparently is. There's nothing else on here that lets you know who made this. So, okay, so we need to check that this is a continuous, positive, decreasing, readily integrable function. It's continuous because it's the ratio of two continuous functions, and the denominator is never zero. So this thing is always well defined. We can take its derivative, right? Oh, wait, we don't need derivative. Sorry, I'm thinking of what I'm doing Cal 1 right now. We can integrate that, right? We will be able to integrate this. In fact, I think if we look at it this way, it's a little easier to see that we'll need integration by parts to do that. And then let me see that it's positive. Okay, how can I determine this is a positive function? Well, n is always positive, right? So this is always positive. Anything is always positive, so it's always positive. Need to make sure it's decreasing. That's kind of the kicker here. How do I show something's decreasing? If I'm looking at a function, I can take its derivative, right? I'm trying to show it's decreasing right now. Derivative of that, I'll do quotient rule, will be e to the n minus e to the n times n over e to the n squared. Everyone feel comfortable you can do that? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. That's the derivative. What am I trying to show about this derivative? What am I trying to show? That it's negative, which would mean the function is decreasing, right? I'm trying to show that this first derivative is always negative. So when I do this, let me try and clean up the top here. 1 minus, I'm factoring out an e to the n. I have e to the n squared on the bottom. And I can cancel some stuff out here, but just let's talk about this. E to the n is always positive. E to the n squared would be positive, right? But what about 1 minus n? Well, if it's either 0 or a negative number, right? 1 minus something bigger than 1. So that's always going to be negative. So we have two positives here multiplied by a negative. That should be a negative number. So I can conclude here that this will be less than or equal to 0 for all n. And again, I'm saying n integers, right? That'll work for all n. So therefore, my function f is decreasing. F is decreasing. How about showing that f was positive? I didn't show it, but are we okay just checking that off? It's positive because it's obviously positive, the original function. And then it's continuous. That was also something I had to check, but I said the ratio of two continuous functions is continuous so long as the denominator is never 0, which never happens. So I think we've met all the conditions, right? As long as we can integrate it. So to integrate this, I'm going to integrate from 1 to infinity. And I'm going to be integrating n e to the negative n dn. And I said integration by parts would work. If we let u be n, dv be e to the negative n. Why am I choosing it this way? Yeah, the derivative of n here is going to go to 1, and then my new integral won't have that n there anymore. So that's why we are employing the integration by parts. I'm just going to set up my table here. The antiderivative of e to the negative n is negative e to the negative n. And so this integral becomes ultraviolet n times negative e to the n. So there's a negative that I pop out here. Here's ultraviolet minus the integral voodoo, but I have a negative inside there, don't I? When I do voodoo, that's negative. So I'm going to make this plus that integral, and that's now e to the negative n dn. And then that becomes negative n e to the negative n minus e to the negative n again, because the antiderivative of e to the negative n is negative e to the negative n. So that's my antiderivative. I want to evaluate that infinity and 1. So first I plug infinity in here. Please remember that this is the same as negative n over e to the n minus 1 over e to the n. All right, that's what that means. Dropping those down. I think it's easier to see this way. If I plug in infinity, what happens? Infinity over infinity. So you do L'Hopital one time, and you get 0. Over here, 0. So when you plug infinity in, you get 0. And then when you plug in 1, what do you get? Well, some number, right? Some number. So I don't even care what it is. It's a number. What does that tell me? It converges, right? This integral converges. And since the integral converges, and it met all the conditions required for the integral test, that means the series converges. Okay, good question. All right, we have much more to do today. I encourage you to come for help if you need help on anything. Get through these homework problems. I mean, I think with integration, all the techniques, integration by parts, all that, hopefully you realize you got to do a lot of the problems, start to get a hang of it. Same thing with these series. You've got to do a lot of them before you start feeling comfortable. P-series. So this is not a, I don't know, you could say this is a test, but it's really like, it's not necessarily a test. It's like the geometric series. Geometric series look a certain way, right? Harmonic series look a certain way. P-series look a certain way. And if they look this way, we'll be able to determine very quickly if it converges or diverges. So here's what it is. If we have a series, n equals 1 to infinity, of 1 over n to the p. Now that's why they call it P-series, because it's actually a series where it looks harmonic, right? Except that p there can be any number. If p is 1, it's harmonic, isn't it? Yeah, because it'll be linear. But if p is 2, it's no longer harmonic because it's squared. So here's the conclusion. That we're not going to prove it because we don't have time to prove this. If p is greater than 1, the series, what do you think? If it's bigger than 1, so like, let's say this is cubed, n cubed. Those terms are going to get small, right? Very quickly. Then that means that this series is probably going to add up to be a finite number, which is the case. The series will converge. But if p is less than or equal to 1, the series diverges. Do you see that this P-series idea actually incorporates harmonic in here now? Like, harmonic is a specific example of a P-series where P is 1. This is a more general statement. This is saying that for any p less than or equal to 1, including negative numbers, this will diverge. If p is greater than 1, it's guaranteed to converge. All right, so let's do an example. Now, I'm going to put this down, C/D question mark. That's me asking you, does this series converge or diverge? All right, that's what I want to know here. 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus forever. So when you're given a series like this, and it's written out in this form, your first goal is to try and get it to look like a summation so you can start playing with it, right? Start to figure out what's going on. So we have to be able to recover the formula from this. So do you see the formula or not? 1 over n squared. Each of the denominators is a perfect square, right? 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and so on and so forth. And then underneath the 1 is 1 squared. So this is summation n equals 1 to infinity of 1 over n squared. There's no magic pill I can give you to make you see these things. You know, I mean, you just have to see them, or, you know, like, I don't know how you saw it. You saw it. You know, I don't know who didn't see it, but, you know, that's just part of the expectation is that you are able to recover the formula. If you recover the formula, then you can start looking at it and going, well, this is exactly a p-series, right? 1 over n squared. This is p-series. So I'm just going to state that. It's a p-series. And p is equal to 2 in this case, which is greater than 1. Therefore, what does the series do? Therefore, I'm going to write this out. Therefore, sum n equals 1 to infinity of 1 over n squared converges, right? Converges. That's the way I'd like to see it on a test. That would be full credit right there. You rewrite it in its form, you identify what it is, you state the condition that allows you to determine convergence or divergence, and you draw your conclusion. The importance of drawing a conclusion here is going to be clear later, because what we're going to be doing is in order to figure out what a series is doing, we're going to be looking at a different series. And then we're going to see what that series does, and then when you say that it converges, then you're going to make some conclusions. So I always want to know what series you're talking about when you're saying it converges. So that's why I threw the whole thing back in here. I want to be very clear. What I'm telling you is that this series converges, which is the original problem. All right? Let's do another one. Converge or diverge on this one? 1 plus 1 over root 2 plus 1 over root 3 plus 1/2 plus 1 over root 5, etc. Do you see it? 1 over root n. Sum n equals 1 to infinity of 1 over the square root of n. And can you rewrite that as a power? Sure. Square root's the same as n being raised to the 1/2, isn't it? And now we recognize that as being a p-series, with p being what? 1/2, which is less than 1, and, well, less than or equal to 1, it doesn't matter. If the p is less than or equal to 1, what is our conclusion? Therefore, this series diverges. And I could bring up the graph of this. You know how I've been showing you like the sequences and stuff, or series, and drawing them for you? I could show you that this does, but just take it on faith. You okay with it? No? All right. Everyone good with p-series? All right, next thing is a new test, all right? This is an actual test. So we have the nth term test, right? If you go off of this sheet, you might want to just put little stars next to what we've done. We've done nth term test, which is where we actually test something, right? We have a geometric series, which isn't a test, but it's just identification, recognition of a pattern within our sequence that looks a certain way, and that means the series does something, you know, converges or diverges. The P series, again, is a recognition thing, and we've already done that. The integral test, it is kind of a test because you have to test the whole decreasing, positive, and you're evaluating an integral, and if the integral converges, then your series converges. So it is a test. You are testing something. We've talked about that. We have not talked about comparison ratio, root alternating, or that last one, okay? So the next one is the comparison test, all right? Now, the way it's stated on that sheet can be kind of difficult to read, so let me try and state it a different way. When we run this test, okay, what we're doing is we want to know if a certain series converges or diverges, okay? That makes sense if I write that? We want to know if some series that we're given converges or diverges. That's what we've wanted to know for the last 2 class periods, right? That's what we want to know. So what we do is we look at a series in which we do know what it does. And what I mean by that, we do know what it does in terms of we know it converges or we know it diverges. But you notice this is a different series, right? A sub n means that I have some sequence and I'm adding them up. B sub n is a different sequence and I'm adding them up. So these are 2 different series, right? So the title of this is comparison test. We're going to try and figure out what's happening with this series. We will compare it to a series that we do know something about. And in that comparison, we will hopefully draw a conclusion. All right? Make sense? All right, so here's what we have. Suppose, I showed you that symbol for suppose? Okay, suppose the series we do know about converges. And A sub n is less than or equal to B sub n for all n. And that for all n might be eventually again, but what's the conclusion going to be? So look, you're taking all these B sub n's, right? All these terms, and you're adding them up. If it converges, it means they add up to be a finite number. If your A sub n pieces in here are always smaller than these little B sub n's were, then when you add all those up, it should be smaller than what this added up to be, right? And if this is a number, then that means then you add those up, it's got to be smaller than some number, which means it is also some number, right? So it should also converge. So if the B sub n converges and this inequality is true, then the conclusion is that the series you are interested in converges. That's one thing that we could do as a comparison test. Now suppose that the series that we know something about diverges. Then can I say the same thing? A sub n less than or equal to B sub n for all n means the other one converges or diverges. So think about this. If I'm telling you that I'm taking all these pieces and I'm adding them up and it's becoming infinite, all right, or not converging to something, and all of my a sub n's are smaller than these, then can you tell me that that one becomes infinite? No, all you can tell me is that what we have is smaller than or equal to infinity. And you can't say equal to infinity, which means that you don't know shit, basically, right? But if I change the inequality around and I say, and your a sub n's are always bigger than your b sub n's for all your n's, now you can say that your series that you were interested in must also diverge, because all your pieces of the series you're interested in are bigger than all of these pieces. Does that make sense? This gets used incorrectly so many times that I want to really make sure you kind of see what's happening here. Yes? Then all that matters is what this one does. That's all that will matter. You always start, remember in what I put here, I said, where is it? We look at a series, right? We look at a series in which we know what it does. You do not want to ever compare two series together where you don't know what either one of them does. You have to know which, you're going to have to pull one from your bank of series that you know about, P series, geometric series, harmonic series, telescopic series, things that you've seen that you know what they do without any thought. Those are the ones you'll pull, and you'll compare that to something that looks weird, right? Does that make sense? So once you know what that one does, when if I pull a harmonic, if I'm going to compare something to a harmonic, then I'm going to be here, right? I'm going to say, all right, I'm going to compare this series that I don't know anything about to a harmonic series. I know a harmonic series is going to diverge, and therefore I need to make sure this inequality is true. If this inequality is true, then I can say now that the series I'm interested in, then the series I'm interested in diverges also. All right, I really hope that makes sense. Are there any questions about it? Any clarifications that need to be made? You want to see it in action, right? So let's see this applied. Does this converge or diverge? How about sum n equals 1 to infinity, 1 over 3 to the n plus n squared? Okay, real quick, nth term test. It goes to 0, doesn't it? What does that tell us? Nothing, right? Tells me nothing. You'll know what I'm saying, right? I'm looking on the inside, real quick, letting n go to infinity. I get 1 over infinity is 0. That test, when that goes to 0, is inconclusive. You don't know anything. That's nth term test. Okay, so then I start looking. Is it geometric? Well, 1 over 3 to the n is geometric, isn't it? 1 over 3 to the n is geometric. But you've got this plus n squared, and you can't just throw that out, right? Can I split this into two different fractions? No, because there's one term on top, 2 on the bottom. Can't split it. What is this one by itself? N squared, 1 over n squared. That would be P series with P being 2, which would converge. And if this one was geometric, if it was, right? If it was just geometric, that would be R is what? 1/3, which would converge also. So maybe it converges, but it's not enough for you to be like, well, it looks almost like a geometric and it looks like a P series, so I think it's going to converge. You have to show this, all right? So comparison. I think it looks pretty much like a geometric to me. I could also say it looks like a P. You know what? Hopefully you're writing in pencil. Let's erase this squared because I want to see with one of them being 3 to the n, geometric wise we said that would have converged, right? And then the 1 over n squared we said that's P series, that would have converged. But now do you see if I erase the squared, that in one direction it looks like geometric, which would converge, but the other one looks what? 1 over n would be harmonic, which would diverge. So now it's not as obvious that this should converge, maybe. I'm just throwing that in there as like a confusion factor. Is that all right? It's good? I've succeeded. All right. Okay, so I need to decide what it is I want to compare this to. And whatever I compare it to, I better know what it does. So what do you want? What are you thinking? You want to compare it to a geometric? Okay, so I get to choose now a geometric. So let me state here real quick what my A sub n is. My A sub n is the sequence inside, right? That's the A sub n. That's the thing inside this summation that I'm going to be comparing something to. The thing I want to compare it to is this. I was told geometric. What geometric do you want me to use? I can use any geometric. Which one do you want? How about this one? 1 over 3 to the n? That's the same as 1/3 to the n, isn't it? Now that's not exactly geometric, is it? Because for geometric, don't I have to have n minus 1 here? But I could make that happen, right? Do -1 plus 1, move things around. The big picture here is r is 1/3, right? R is 1/3. This is geometric. I have an r that's 1/3. That's less than 1. Therefore, this series does what? Converges, right? Okay, so I have chosen a geometric series to compare my series to. I've chosen it to be a geometric series that converges. And I chose it to be 1 over 3 to the n because that's very close to what I have up there, right? The only difference is that plus n there. Y'all with me? Okay, according to what the test says, let me see if this makes sense. I don't really like, yeah, let's go off of this one. On the comparison test, we're looking at the b sub n. I didn't put what b sub n was here. Which one is b sub n? This one right here, right? So our b sub n is 1 over 3 to the n. The comparison test says that if our series of b sub n, that's this one, if it converges, which it does, what is it that I need to show? It says if it converges and what? A sub n is less than b sub n. So I need now to show, I want to show right now, I want to show a sub n is less than or equal to b sub n, right? That's what I want to show. So let me show it. If it might not be true, okay? That's if I can show this is true, I can draw the conclusion of the test. The conclusion of the test would be that the series that I'm interested in would also converge. So put your a sub n down here, which was 1 over 3 to the n plus n. Is that less than or equal to 1 over 3 to the n plus n? Oh, sorry, hold on. What the hell did I just do? Just 1 over 3 to the n. Is that true? Is that true for all n? All n greater than or equal to 1. So I said last time, just kind of mess around with this cross multiply type thing. It is, I think, after you get used to this, you'll see that, I mean, at this point, these are exactly the same expressions except for this one has plus n, which means that the denominator on this one is a little bit bigger than that one. And since they both have 1 up top, that means that fraction's smaller than that fraction. But let's just do it this way. It's, you know, until we're really comfortable with it. This is this. Subtract 3 to the n on both sides. And you get 0 less than or equal to n. Is that true? Yes, that is true. I multiplied both sides by this, right? By the common denominator on both sides to get from here to here. So this is true. So I had a series that was convergent that I compared. This inequality held true, which is what I needed for the test. Therefore, the test tells me what? Therefore, by the comparison test, what can I say? Summation n equals 1 to infinity of 1 over 3 to the n plus n does what? Converges. Do I know what it converges to? No. I know it converges, though. Questions? Now, up here at the beginning, I changed that n, right, squared over to an n. What if you had wanted to compare it to a harmonic? What if you wanted to, right? Let me show you what would happen if you compare it to a harmonic. So I'm going to do the same problem, but I'm going to choose a different series to compare it to. And let's see what conclusion we draw, all right? So same example. So in this problem, I have a sub n is 1 over 3 to the n plus n. And I'm going to say I want to look at this series to compare it to, because I know that that series is harmonic. And therefore, it does what? Diverges, right? That series diverges. You with me? So the b sub n that I have here is 1 over n. Now, what does the test say for comparison? If you come in and the series you're going to compare it with, if it what? Diverges, then the inequality that needs to hold is what? So I want to be able to show that a sub n is greater than or equal to b sub n, right? That's what I want to be able to show. So what is a sub n here? 1 over 3 to the n plus n is greater than or equal to, what is b sub n? 1 over n. Okay, let's see what happens. Do your little cross multiply here. You get n is greater than or equal to 3 to the n plus n. And that, subtract n on both sides, you get 0 is greater than or equal to 3 to the n. And that is not true. Yes, that is correct. That is false. What does that tell you? Okay, so let's go through this. We had a series, we didn't know what it did. We compared it to a series that diverged. We did the thing that's required. We had to show that this was bigger than this, but weren't able to show it. That does not mean that this series does the opposite of what this one does. It means that you just had a nice exercise in inequalities and you have no result and you know nothing. Okay? It means that the series that I used to compare with didn't give me anything, was not valuable. The series I chose did not work. The test does not work for that series. Does that make sense? In order for the test to work, if you've got a divergent series, this inequality must hold. If it doesn't, you got to pick something else. You got to pick a different series to compare it to. So maybe I would have done this and said, oh, wait, that didn't work. Maybe it converges. Let me compare it to something that converges, like geometric. And that's what we did right before this, right? Understand? But you can't say, just because this didn't work, that it automatically converges, because it still could diverge, just not because of the comparison with that series. So those are the things I'm looking for on a test, okay, on an exam. Is someone applying the test correctly and drawing the correct conclusion. So I would say for this, like, test fails. Start over. Try something new, right? So I'm thinking that there might be like a take-home set of problems that I'm going to give you, because these take so much time. I mean, it would be one of those issues where in class, I could only give you maybe 4 or 5 of these, maybe, and with the other stuff too. And so, so if I give you something to take home, what I'm looking for is I'm looking for you to write down all your work, including the things that you run into that don't work. Like, I want to see, okay, I tried this, didn't work. Tried that, didn't work. If you get it the first shot, you get it the first shot. But, showing that you're actually going through a procedure here is an important thing for me to see. All right, let's look at something else. I'm only on, that's the first page of an eight pages of notes today. Let's see how we do. Okay, how about this one? New problem. Sum 10 over 7n cubed plus n squared plus n. I'm going to go a little quicker through this now, right? What's the first test that you might run? Nth term test? Fails, right? All right, it's not geometric. It's not harmonic, although there is a harmonic way down there at the end. There's an n, but there's a bunch of other stuff too. It looks p-series also with the n cubed, the n squared, and the n. Not telescopic? Well, maybe. Because with telescopic, didn't we like factor and then do like partial fractions? Oh man, I don't want to do that though. Instead, I think what I'll do is do a comparison test. Could I do integral test? Would you want to find the antiderivative of that? Probably not. Because again, you'd have to factor and do partial fraction decomposition to be able to factor it. So, I mean, to be able to integrate it. So I'm not a real big fan of anything but comparison test. And I'm thinking of it because it looks a lot like a p-series, right? That n cubed is like p-series. The other stuff at the end probably isn't affecting the sum too much as that n cubed, right? So let's try that. I'm going to say that this series, the sequence I'm going to be comparing here is the one that's in there. I'm going to look at this series here. What should I pick? How about just the 10 over 7n cubed? By the way, I could just pick 1 over n cubed. You can try it yourself on your own time. You could just go 1 over n cubed. It would work the same way. Because remember, the constant shouldn't affect, a constant can come out of the series if it converges. So it doesn't really affect things. But I think by me choosing that, I'm trying to get you to see that what I'm focusing all my attention on is that piece right there. That's what is influencing me, or what's the word I'm looking for? I don't know. Guiding me to use that, influencing me to, where's the word? What is that? I'll think of it in a second. Sorry, my brain's not wanting to work right now with English words. Okay, that's what I'm going to use, right? What do we know about this series? We can take the 10/7 out. It's 1 over n cubed. That's a p-series. P is equal to 3. Therefore, it converges, right? So I am going to compare the series I'm interested in with a convergent p-series. What do I need to be able to show, right? What do I want to show in order to make this comparison test worthwhile? What? That a sub n is less than or equal to b sub n, right? Because I'm trying to show the convergence. So I want to show a sub n is less than or equal to b sub n. If I can show that's true, I'm done. So 10 over this, 7n cubed plus n squared plus n, is that less than or equal to 10 over 7n cubed? And you could do your cross multiplying again, right? I can divide both sides by 10 also. But if I do like a cross multiplication, I divide by 10. I get this. And then I can cancel out the 7n cubes on both sides. And 0 is always less than n squared plus n, because n is always 1 or 2 or 3 or 4 or 5, so that should always be true. So I've shown what I wanted to show, right? Therefore, the conclusion is sum 10 over 7n cubed plus n squared plus n converges by the comparison test. Now, I'm putting here at the end what I did, right? I'm including the test I ran. You might get into the habit of, as soon as you know what you're going to do, writing up here, comparison test, right? And then from there, run the test. Because if your test is inconclusive, you might go to a different test after that. And so you go and you try after that the ratio test. And that doesn't work, so you go and you use the whatever, So just kind of breaking up your work into separate sections. The only reason I didn't put it up here is because we are talking about the comparison test. I'm giving you examples of the comparison test, so it's kind of obvious what the test is, right? Next one. N cubed over n to the fourth minus 1. N equals 2 to infinity, because I can't have 1 in there. Real quick, first test I like to run is what? Nth term, what happens as n goes to infinity? Infinity over infinity. So you do L'Hopital's rule, you still get infinity over infinity. Do L'Hopital's rule again, you get infinity over infinity. And what happens every time you do L'Hopital, the powers come down. So eventually you're going to get something that looks like 1 over n. And that'll go to 0, which means you don't know anything. Right? So n-term test fails. Doesn't look geometric, doesn't look telescopic, doesn't look like a lot of things, but comparison, right? Anybody want to assist in the comparison? This is the part you have to figure out. If you're going to do comparison test, you could do integral test. Yeah, integral test might work too, because if you let that be u, then that's du up there. So I see integral test here also. I just don't, the reason I don't like the integral test, there's a lot of things you have to show, and then you have to integrate. With the comparison test, as soon as you show that inequality is right, you're done. So, what's that? 1 over n as your b sub n. Okay, that's correct. But what I want to make sure, I don't want you focusing just on the end of the fourth and saying, oh, it's p series with 4. I'm going to compare it to a p series with p being 4. Because the n cubed on the top has an effect on things too. Essentially, this thing very much looks like n cubed over n to the fourth, right? The minus 1 there has a very, very minimal impact when we're talking about huge n's here, right? If you're way, way out, n is, in the trillions, minus 1 on the bottom doesn't really mean much, right? It's going to behave very much like n cubed over n to the fourth, which is the same as 1 over n. So that's the one we want to compare it to, 1 over n. And again, it's kind of like you're taking a swing at it, right? I mean, you think it's 1 over n, let's see what happens. What do we know about this? Harmonic diverges. And so what is it that we want to show? For divergence, we have to show the inequality A sub n must be greater than or equal to B sub n. Oh, I didn't write down what A sub n and B sub n were. A sub n was the one from up here, right? N cubed over n to the fourth minus 1. What's the B sub n? 1 over n. All right. Is n cubed over n to the fourth minus 1 greater than or equal to 1 over n? Little cross multiplication, n to the fourth greater than or equal to n to the fourth minus 1. I said cross multiplication. I hate when people say that. I'm sorry. Subtract n to the fourth on both sides, and you get 0 is greater than or equal to negative 1. Is that true? Yes, it's always true. Therefore, our conclusion is that our original series did the same thing that the harmonic one did, so this diverges. Now, I'm not going to put by comparison test. Why am I not writing by comparison test? Because up here I put comparison test. So I kind of told you what I was doing, and therefore, if someone were to come back and be reading my work, like someone wanted to give me a grade on it, then they would know from this what I was doing, so they would know the conclusion I drew and why I drew that conclusion. Curious to see what would have happened. Do I need to go back? Y'all still need this? Anyone need this? What would have happened if you had not picked up on that? What if you had not picked up on that and you came in and tried to compare it to this? And you said, I'm going to compare it to a P series with P is 4, and I know that that converges, right? Then what inequality would you have to have shown? Less than or equal to B sub n? That's what I would have had to have shown for the convergence. So I would have needed to show that the n cubed over n to the fourth minus 1 had to be less than or equal to 1 over n to the fourth, right? And when I cross multiply and do things here, I said it again. I would have to convince you that n to the seventh is less than or equal to n to the fourth minus 1. What do you think? No? Never? I mean, how would you convince yourself? I mean, you could look at it, but right? I'm just saying, like, n to the fourth times n cubed is bigger than n to the fourth, isn't it? Because n is 1 or 2 or 3 or 4. So this is always going to be bigger than that. Subtracting 1, it won't matter eventually, right? It won't matter eventually. So is this true? No, that is not true. This side is not smaller than this side. It's the other way around. Therefore, this test fails. Well, the test doesn't fail. Your comparison series failed to tell you anything. The test may still work if you try a different series like we did right before this. So failed, fail. All right. Now, within the comparison test is another test. It's if you look at your sheet on comparison, it said part A, part B, or sorry, part 1 and part 2 was if B sub n converges, then if B sub n diverges, and then look at the third one. It says if limit n goes to infinity, blah 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 blah. That thing, yes. That in some books is referred to as a completely different test. And on that sheet, it's included in the comparison test. So I'm going to write it as a different test, but realize what I'm talking about is right there, part 3 on this sheet. It's called the limit comparison test. And I need to correct something. It's not technically wrong. I just forgot to put something in somewhere. Hold on. Go back to when we first wrote the comparison test down. Where is it? There it is, right here. All right. When we are here, when we're doing the comparison test, all right, it's not as important right now as it's going to be in a few minutes. When we do a comparison test, both the A sub n and B sub n's, both of these have to be positive, meaning that this test will not work if we have an alternating series where we have positive and negative terms in there, which is coming later. Right now, conveniently, every series I've given you today, when you look at the terms, none of them were ever negative, right? Like we never had a -1 to a power to make it alternate. That never happened. And that's written on your sheet. It is here. On the comparison, right underneath the series, you see where it says A sub n greater than 0, B sub n greater than 0? It's there, but I forgot to write it in my note. Okay? Yes? All right, go back to where we are here now. Limit comparison test says, again, it's the same conditions as the comparison test. We want to know what this guy's doing with A sub n greater than 0. I'll state at that time. We want to know what that guy's doing. We want to compare it B sub n, B sub n greater than 0. And what is it about this B sub n? We know what this one does, right? We know this one's behavior. So it's the same exact thing as a comparison test. We want to know what the series does, so we compare it to something that we do know about. But the way we do the comparison, instead of doing that inequality, we do this instead. If the limit as n goes to infinity of A sub n divided by B sub n equals some constant c, which is greater than 0, and finite, that's important, and finite, meaning that that limit, when you take this limit, you cannot get infinity. All right, if you get infinity, this limit comparison test fails. If you get 0 in this limit, this test fails. If you get a finite number, then the conclusion is this. If that limit is a number greater than 0, then whatever B sub n does, this one does. So whatever the B sub n does, A sub n does. Why do you think this works? Think about what this means geometrically. Let me try and draw a picture. I'm going to draw B sub n first. I'm going to draw it in blue. B sub n. And let's say that B sub n, when we add these things up, it diverges, goes to infinity. Right? So, right, let's say it does that. The limit comparison test says that when you look at the ratio of the terms, A sub n divided by B sub n, right? When you look at that ratio. So let me put an A sub n in here. The ratio is let's say the a sub n divided by this one, right? So do you agree if I take that black dot, whatever the value is, divided by that blue dot, I get a number? Yes? And then when I divide this black dot by this dot, that number would be bigger or smaller than the first one? The ratio should probably be smaller, right? What this is saying is that if the ratio of the two becomes constant, that means the distance between them is holding, right? It's holding together. And so that if the b sub n takes off and goes to infinity, and the a sub n has to stay within a constant ratio of it, then it's going to go to infinity also. Or if the b sub n converges down to something, then the a sub n's got to go with it and stay within that ratio, then it's going to converge also. Kind of make sense? That's what's happening here. All you need to know how to do is to apply it. So let's take a look at a problem. Converge or diverge? Real quick, nth term test. Fail, right? Okay. Geometric, no. Harmonic? If I were walking in off the street right now, I would be thinking comparison test with harmonic right now. Compare that to 1 over n, right? It's going to diverge. I'd have to show the test. So this could be done with the comparison test that we just did. But I want to show you can also do it with the limit comparison test. And you could probably even do it with the integral test. Because you could integrate that, right? 1/4 natural log 4n plus 5, something like that. But let's just see how nice this limit comparison is. So I'm going to do limit comparison. I'm going to try and compare it to, I'm going to compare it to a harmonic. So I'm still picking that harmonic. It's just the way that I'm going to actually do it is going to look different. Instead of comparing a sub n and b sub n in the inequality, I'm just going to take a limit. I'm going to take the limit as n goes to infinity of a sub n, which is 1 over 4n plus 5, over b sub n, which is 1 over n. Yeah? And then just flip things around. N over 4n plus 5. That's infinity over infinity. You take L'Hopital's rule one time. And you get what? 1/4. And that's equal to a constant, right? Which is greater than 0. It's a finite number. Well, it's equal to 1/4, but. Pardon? Right here? Did we? Or? Yes. You don't have to use L'Hopital. Yeah, you don't have. You can just divide everything by n, still same result. So that means that this test works, right? This test holds. The conclusion can be drawn. Therefore, the series we're interested in will do whatever you compared it to did. And I compared it to a harmonic. So that harmonic diverged, so this one diverges. Since 1 over n diverged. Questions, comments, concerns, gripes? If you would have used what? What p-series? Like, oh, if you would have said here? Yeah, with p-series, p being 1? Yeah, that's fine. Okay, how about this one? Sum equals 1 to infinity n plus 5 over the cube root of n to the 7th plus n to the 3rd. I think there's a lot of things you can throw out here, right? Harmonic, it's not harmonic, it's not geometric. Nth term test, first test. It's not as obvious, but I don't think it's going to work. Oh, I don't want to integrate that. Comparison. See, the limit comparison and the comparison test are the same thing. You still have to find something to compare it to. It's just the way you compare it is different. So what do you want to compare this to if you want to do a comparison? 1 over n to the 3rd? Yes? No? 1 over n? So what are the overpowering terms in the numerator and denominator? We have n, and then on the bottom, the overpowering term is this, right? But cube root of it. So that's kind of the pattern of what we've been doing this whole time, trying to compare it to. We've been looking at the highest power up here, highest power down here, and then kind of making a ratio out of those. So what if we try a series where the n, we have an n on top, but on the bottom we have like the cube root of n to the 7th. But hold on, do I even know what that does? Yeah, I got to mess with the power a little bit, all right? This is the same as n to the 1st power over n to the 7/3, which is 1 over n to the 4/3. So you got to do some exponent properties there, and 1 minus 7/3 is negative 4/3, and then you bring it back down. And what type of series is that? P series. P is 4/3, so it converges, doesn't it? Since it's greater than 1. So I'm going to try. I'm taking a swing at it, and I know it's going to work because I already worked this problem out. But it's going to work. I'm going to compare that thing up there to a convergent P series. Now I just need to choose. Am I going to do it comparing it where I do the inequality comparison or the limit comparison? And it's your call. I mean, there's no, definite right way. But since you have only seen limit comparison once, let me try this one with limit comparison. So our A sub n is this, right? Our B sub n is that. So what is the limit as n goes to infinity of n plus 5 over the cube root of all this stuff? Not real happy about this. That's A sub n all over B sub n, which was n over, well, do I really want that? Do I want to keep it like that, or don't you want to go 1 over, you want to do it to this right here, like take it to here? Yes? You okay with that? If I just, instead of writing this down, can I just write this? Okay. 1 over n to the 4/3. So flip it up, right? Flip this thing up. Its limit n goes to infinity. This n to the 4/3 comes up here next to the n plus 5. So I have n to the 4/3 times n plus 5. And on the bottom, all I have is cube root of n to the 7th plus n cubed. Crap. All right, that's it. Just what happens is n goes to infinity there. So you have infinity over infinity, don't you? Anybody feel like doing L'Hopital's rule on that? No. So this is where the value of coming in and dividing through by something is more powerful than L'Hopital. Before you learn L'Hopital, you try and divide through by something that you basically want the highest power in the bottom to turn into a 1. That's your goal, is to make this guy turn into a 1. And then you learn L'Hopital and think L'Hopital is always going to save you. This is a problem where L'Hopital doesn't save you. So how can I get this n to the 7th to turn into a 1? I've got to divide it by n to the 7th, right? But the only way to get an n to the 7th inside a cube root is to start with it out here and force it inside, remembering that as things go into cube roots, they get cubed. So how about I choose this? Come in here with 1 over n to the 7 thirds. And whatever I do on the bottom, I have to do it on the top. Right? What's going to happen if I take 1 over n to the 7 thirds and I force it into a cube root? It gets cubed, right? When you cube 1, it's just 1. When you cube 7 thirds, you're multiplying 7 thirds times 3, which gives you 7, right? If I do 1 over n to the 7 thirds and I cube it, or cube it when it goes in, it gets cubed, then that's 1 cubed over n to the 7 thirds, but then cubed. You multiply those two powers. 7 thirds times 3 is 7. So that's going to give you, when this goes in this cube root, it's going to turn into a 1 over n to the 7th power. All right. Let's go ahead and look at the bottom. I'll get back to the top in a second. I still have the cube root. When that went in there, it went in here as a 1 over n to the 7, so I'm basically doing n to the 7 under both of these, right? That's what's going to happen. So that'll turn into a 1 plus 1 over n to the 4th. Okay, that's what happens here. On top, though, what do I get? I have to multiply this times this one, right? What's 4 thirds? N to the 4 thirds divided by n to the 7 thirds. This is n to the 4 thirds, take away 7 thirds, which is negative 3 thirds, negative 1. So this is just 1 over n, isn't it? This is just 1 over n. Take 1 over n and put it in here and here. And what do you get? 1 plus 5 over n. This is just properties of exponents, right? That's all this is. I say that in a way that I'm not trying to belittle it, because I understand that's part of the issue, part of the problem is that people get hung up on that. But at the end of the day, it is a college algebra topic, right? All right, so now let n go to infinity, and what do you get? 0, 1, right? And then 0, 1, so cube root of 1 is still 1. So you just get 1 here, don't you? This whole limit is 1, which is a number that's bigger than 0, right? It's a constant. It's bigger than 0. It's finite. That's what you need for the limit comparison test to work. So because of that, your conclusion is, therefore, series n plus 5 over cube root n to the 7th plus n cubed must do what? Does whatever the one we compared it to did, which was what? Converges. And this was all underneath, did I tell you what test I ran? I never did. By the limit comparison test. It's a little yucky there with the algebra. I probably just would have gone and dropped the class. No, I'm just kidding. I don't know. Yeah, probably. I mean, yeah. I don't think there's. Well, I'm not saying by comparison. I'm saying by limit versus. Well, probably not. I probably would have tried the other comparison, but then something tells me that inequality is not going to be easy to convince myself that it would be true, because I would be comparing a sub n, which would have been that n plus 5 over that cube root n to the 7th plus n squared, right? And I would have been comparing that to, it converged, right? So I would want to show that that's greater than or equal to the other one, which was 1 over n to the 4/3. So if I multiply both sides, you see that this inequality is going to be kind of messy. I don't know if I could really convince myself that that would be true. Yeah. Yeah. Did you try it? Were you convinced or kind of? Yeah. Yeah. It's not simple. It would be hard to convince a reader. The limit there is very definite, right? I mean, it showed the ratio as a constant. You're done. So, good question. All right. How about? I thought I had one more in here. Oh yeah. Never mind. It's coming. All right, we are in 8.4 now. We're moving into 8.4. I'm not even going to really write down that we're in 8.4 because to me this is all the same. I mean, it's continued more tests, but now we're going to allow our series to be alternating series. So let's just make sure we understand a couple of definitions. Definition here, alternating series. An alternating series is a series where your terms alternate in sign. You know, positive, negative, positive, negative, positive, negative, or you could start negative, positive, negative, positive, negative, positive. Either way, no matter what, any alternating series should be able to be written like this. So if you have a series, and we did this when we first started talking about sequences, I said if it switches signs, you can always take care of the switching of the signs with the little -1 to the n, right? We said sometimes you could use n plus 1 if you wanted to start, you know, in a certain place, right? You can change that to make it start positive or negative. But the -1 is the key to making something alternate signs, right? The rest of it can just be a regular sequence like, you know, harmonic or geometric or whatever, right? So the way we can write an alternating series is you take care of the alternating part with the negative and then guarantee me that everything that's left will never be negative. So that this part's the switching of the signs, everything else is always just a positive, 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 positive. Is that okay? Do you all agree I could do that? All right, that's what an alternating series is. So they look like this. It's going to be either like A1 minus A2 plus A3 minus A4 plus A5 forever, or if you wanted, if you had to start at negative, then it can do this also. Right? That's basically what an alternating series is going to look like. You're adding up terms forever, but it's like you add something, subtract, add, subtract, add, subtract, add, subtract, and the question is, does it converge, does it diverge? So we have a test that we can use to check for convergence and divergence of specifically alternating series. And it's a great test, all right, because it's relatively easy to apply. It is called the alternating series test. The great thing about the alternating series test is that it's kind of clear when you use it, right? When you have an alternating series, you want to pull this test out. When you have an alternating series, you cannot do the comparison test, because the comparison test requires that your sequences be positive. That part that I left out at the very beginning, okay, that's why you can throw that out when it comes to an alternating series, because comparison won't work. So let's see what the test says. It says, suppose we have a series that's alternating. And I'm not even going to specify where it's starting from, okay? It could be negative first, then positive, or positive, then negative. As long as it alternates, doesn't matter which comes first, negative or positive. As long as it's alternating, okay, then if these two conditions hold, first of all, if a sub n is greater than or equal to a sub n plus 1 for all n, and 2, the limit as n goes to infinity of a sub n equals 0, then the series converges. That's the test. So what we have to do is we have to take our alternating series, get a formula for it, split off the part that's not changing signs, that's our a sub n, that's this piece, and make sure that a sub n is greater than a sub n plus 1. That means that the sequence is decreasing. The nth one is bigger than the next one, which is bigger than the next one, which is bigger than the next one. So it's a decreasing sequence of numbers, and that they are going to 0. That's a great test. It does not work for regular series. It only works for alternating. I mean, think about a harmonic series. Think about a harmonic series. 1 over n, right? This is 1 plus 1/2 plus 1/3 plus 1/4, right? Is this a decreasing sequence? Are these numbers getting smaller, right? Is the one before the next one bigger, right? 1/2 is bigger than 1/3, is bigger than 1/4, right? So that is true. Are they going to 0? That's the nth term test. Are these going to 0? Yes. For an alternating series, that means it converges. But if it's not alternating, can't do it. See, this isn't alternating, so we couldn't apply that test. So it's nice that this is all we'd have to show for an alternating series. Okay, here's an example. Convergence or divergence of this. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus ... What does your gut tell you here? What does that look like to you? That looks like 1 over n, right? It looks harmonic. Harmonic series diverge, don't they? Like a regular harmonic diverges. So your gut may be telling you this is going to diverge. But it's an alternating series. That's different, all right? So let's look and see if we can come up with a formula first. So this is summation n equals 1 to infinity. I know I've got 1 over n, right? I know that that's happening. But how do I get it to alternate? I need to put a negative 1 to what power? N plus 1. I need n plus 1 because I need my first one to be positive and then my next one to be negative. That's not going to matter, okay? That's not going to matter as much, but you still need to pull the negative and identify it, the negative 1 out here. I do want you to get the right power. It's not too much to ask. I'm just saying it's not going to affect our ability to get an answer here. Okay, so the part of this that we are going to be looking at, our A sub n is 1 over n. And now the test, all right? This is an alternating series. I look at this part of it and I try and show two things. The first thing I have to show is that A sub n is greater than or equal to A sub n plus 1. What is A sub n? 1 over n. Okay, is that greater than or equal to A sub n plus 1? So A sub n plus 1 is the next one. The next one after 1 over n is 1 over n plus 1, right? So just replacing n with n plus 1. Is that true? Yes, do your little manipulation of this. 1 is greater than 0, that's true. So that's the first thing I have to show. The second thing I need to show is that the limit as n goes to infinity of A sub n, which is 1 over n, is 0. And it is, right? That limit goes to 0? Check. Both things that I had to show were true. It was a decreasing sequence of numbers. They went to 0. And the fact that it was alternating means that by the alternating series test, we know that this sum converges. So that's a good example, because if that series is not an alternating series, right? 1 plus a half plus a third plus a fourth, it's harmonic and diverges. But if I do it as an alternating series, it converges. It's kind of interesting that it does that. Next one. Tell me about the convergence or divergence of this one. Hey, you gotta wake up. This is in high school. You were asleep. You're asleep now. I find that disrespectful. I mean, if you knew this, if you could answer, does an alternating harmonic series converge or diverge right now? Can you answer that question? Okay. All right. What about this one? Alternating, right? It's obvious because I gave you the negative 1 to the n, so it alternates. Look at the A sub n. This would be this piece, right? That's our A sub n that we need to investigate. So I'm going to use the alternating series test right now. I'm going to try and show two things. The first thing being that A sub n is greater than or equal to A sub n plus 1. So what is A sub n? 3n over 4n minus 1. Is that greater than or equal to, now you have to replace the n with n plus 1. So 3n plus 1 over 4n plus 1 minus 1. And that inequality is going to take a little bit of work, right? But I could do it, right? Let me try this. 3 over n, or 3n over 4n minus 1. I'm just going to kind of multiply some stuff through. 3n plus 3, 4n plus 3. So I'm just distributing my 4 through, subtracting 1. Now I'll do clearing of the fractions. Oh my goodness. Is that really going to be this? 12n squared plus 9n greater than or equal to 12n squared. I'm doing like a FOIL here, right? This one times this one. So I'm doing this times this times this. So negative 3n plus 12n. So I can't do simple math right now. Is that right? Plus 12, but then we had minus 3, didn't we? That's it? Okay. Now cancel out some stuff. Oh, wow. 0 is greater than or equal to negative 3. That's true. It's decreasing. So it converges? Not yet. Okay, we have one more thing we have to show. I need to show that the limit as n goes to infinity of 3n over 4n minus 1. 4n minus 1? Yeah. I need to show that that goes where? To 0. Infinity over infinity. So L'Hopital gives you what? 3/4. That's not 0. Which means the test fails. Does it mean that it diverges? No, it means the test fails. Test fails. Which means that you have to figure it out a different way. Well, I did something on this problem intentionally because I wanted to just show you, I need to show you this work. I wanted to show you this work. I wanted to show it fail. But what is it that I had been normally doing this whole time whenever I'd start a problem? What was the first thing I always tried? The n-term test, right? The n-term test. So I want to show you something real quick. If I were to do the n-term test on this, which is what I should have done to start the problem, I would have been trying to find the limit as n goes to infinity of the original series, which would have been this, right? Now, as n goes to infinity, negative 1 is going to swap back and forth positive, negative, positive, negative, positive, negative. But this other part, we just said this other part is going to head towards what? 3/4. So this is kind of headed to limit as n goes to infinity of negative 1 to the n times 3/4, if that makes sense. What does that look like as a sequence of numbers? Back and forth, 3/4, back and forth. So it looks like my sequence, not my series, my sequence is doing this. It's doing something, it's going, you know, positive, negative, positive, negative, positive, negative, but they're getting closer and closer to positive and negative 3/4. Right? There's like a convergence happening where they're jumping back and forth. So it's almost like it's jumping back and forth between 1, negative 1, 1, negative 1, 1, and that series diverged. Right? So I could have concluded it from the n-term test that because this is divergent, right, it goes somewhere other than 0, right? The conclusion of the n-term test, it diverges if the limit is not 0. So I could have concluded in the very beginning this was divergent. But it is not divergent because this failed. It's only divergent because I showed it's divergent. There's a difference. we're almost at a good place to stop. 10 minutes. See what you think about this one. Can't believe we're like, what, 2 weeks away from Thanksgiving or something like that? Is it 2 weeks today? Jeez, it's crazy. Again, the alternating part of this is the thing that's kind of going to clue you in. Can I do a quick nth term test? The top is n, the bottom is like square root of n cubed. Divide everything. It's going to be 1 over infinity, basically. It's going to be 0. So I'm not going to do it, but you could show that that goes to 0, which is inconclusive. But the fact that it goes to 0 is actually good because it's an alternating series, right? So let's look at this part right here as a sub n. And the first condition for the alternating series test is to show that a sub n is greater than or equal to a sub n plus 1. And I think that's going to be a little bit of a challenge. N over square root of n cubed plus 2 must be greater than or equal to n plus 1 over square root of n plus 1 cubed plus 2. That looks like a mess, doesn't it? So I'm going to do something that we did before that's going to help us out here. And squeeze would work if we were trying to show that this was going to a certain place. I can already tell you where that's going. That's going to 0, that's going to 0 if I let n go to infinity. But instead of, what else did we use when we were trying to show a sequence decreased? Instead of looking at it as an inequality, as a function, and then showed that the derivative was negative. That's always in our toolbox now. If this inequality looks challenging, instead show that f of n is decreasing, which really means I need to show that the derivative is less than 0. Right? That's what it means. So turn it into a function of n, which means we have n over the square root of n cubed plus 2. And I know you're probably looking at that saying you don't really feel like taking the derivative of that. And I'll look right back at you and say, well, I don't feel like trying to figure out what that is either, because that doesn't look any more interesting or fun to me at all. So if I'm going to take derivative of this, I would say quotient rule. Derivative of the top is 1 times the bottom minus, now the derivative of the bottom is going to be a square root, but then you have to go inside and take derivative of what's in there. So derivative of the square root of something is 1 over 2 times the square root of that something. So I get 1 over 2 times the square root of that something. Then chain rule says times the derivative of what was in here, which is 3n squared. And then finishing off the quotient rule times the top function, which was n. So that's all just the top. And then we divide the whole thing by the bottom squared, but it's a square root, so that's nice. And what am I trying to figure out with all this mess? If it's positive or negative, right? Positive or negative? Okay, well, is that positive or negative? Now you have to be careful here, okay? Because I've been sitting here going, oh, this is positive, that's negative, right? Look, we have subtraction between these two, don't we? If you tell me that this is positive and that's negative, is that enough to tell me that's negative? Or, I'm sorry, if you tell me that that's positive and that's positive, you subtract them, is that negative? You don't know, right? We can do it with multiplication, but we can't do it with addition and subtraction, generally. So what I need to do is try and put these two together. So I need a common denominator between these two. So it'll look like, what do I need? This right here is on top, really, as a 3n cubed. Get rid of it. So what's my common denominator? The 2 times that square root thing. So I'm going to introduce it here and here. Or you can multiply the entire fraction on top and the fraction on bottom by this. It's really your call. I'm going to just introduce 2 root n cubed plus 2 on the top and bottom right here. And when I do that, I get 2 times n cubed plus 2 on the top. Okay, that's what happens when I put these two together. And then minus this right here, minus 3n cubed, over the common denominator, which was 2 square root n cubed plus 2, all of that over the other denominator, n cubed plus 2. And now I can start talking about the signs of things after I clean up the numerator. What happens when I clean this up? I get 2n cubed plus 4 minus 3n cubed, right? 2n cubed plus 4 minus 3n cubed. What is that? 4. That's right, yes. We could write it either way. That, then over. Now tell me about this right here in terms of its sign. N cubed plus 2, positive. Square root of positive number is positive, times 2, positive. So we have positive here, over. And then this right here, n cubed plus 2 is positive. And then 4 minus n squared, definitely a negative number, right? Well, not always, right? If n is what? Bigger than 2? Or 2 or higher? 2 or bigger? If n is 2 or greater, then this is going to be true. If n is greater than or equal to 2. Which it's not initially, right? It's not initially. At n is 1. So it's not initially decreasing, but eventually it's decreasing. So I have shown that it's decreasing. First condition's met. Second condition is take the limit as n goes to infinity of this right here. Limit, this is my second condition, n goes to infinity of n over square root of n cubed plus 2. So this is where I introduce that thing, and I'm not going to do L'Hopital. I'm just going to come in here. I'm going to go 1 over n cubed 1 over n to the 3 halves. Sorry. Can you all see that? 3 halves? Because when it comes in here, it gets squared, and that'll become a 1 over n cubed. And then do the same thing on top. I'm not going to go through the work. This will turn out to be 0, which checks off. Therefore, it converges. All right. From your homework last time, what did I assign through? I had given you on page, well, let me just tell you, on page 443, I don't recall what I had given you. Okay, so you should be able to do 7 through 28. Oh, you did do 7 through 28 all? Okay. That's where okay, so you should be able to do that. And then now on 453, you should be able to do everything here too. Page 453, anything from 6 to 30. are all fair game. Now, what you don't have on these 2 pages of homework, what you don't have yet is alternating series. So I started alternating series, showed you a few examples here, but this homework does not include the alternating series. And that's because the alternating series, well, do you want some homework from alternating series? There's a few things in alternating series we haven't talked about. But I think you could probably get away with doing these without any issues. No. We'll just stay away. Yeah, because the next section 8.4, we still have, what tests have we not done? Ratio root, right? We haven't done the ratio and root test. And we haven't talked about absolute convergence yet, so we'll save that for next week. We should be done with our series tests next week. Next Tuesday. And then on Thursday, we'll start power series, which we actually start to look at series of power functions, which is where this all came from, right? The whole idea that you could rewrite e to the x as something plus something plus something, but they were all powers of x. Now we start to actually look at series of, instead of numbers, series of functions. Okay, have a great weekend.